Yeah, welcome to the LiPLANET training regarding the electrode and cell production. To kick us off, I want to shortly introduce you into the basic setup of lithium-ion batteries and their production process, and then we will go deeper into the individual process steps. So, a lithium-ion battery cell consists of two electrodes, an anode and a cathode. These electrodes contain the lithium and therefore energy storing materials. Here shown in gray on the anode side and in blue on the cathode side. Then we have the separator, which prevents the electric short circuit between those two electrodes. But to close the circuit in the cell, we have to have the lithium ion diffusion. And this is done by the electrolyte, which is shown here as the orange tone throughout the cell. The cell voltage and its capacity is mainly defined by the active material and the respective specific electrode combinations. So how much active material do I use and what other components are in there, how thick are the electrodes, and so on. A high active material amount is favorable to increase the specific and volumetric energy of the battery because we have less inactive, non-energy storing materials, and therefore we can put more energy into the same space. The electrodes in such a cell on their own are quite complex in their structure. To allow for the energy storage, we have to bring the lithium ions and the electrodes to the same active material spot. And therefore, because of this, the electrodes of lithium-ion batteries are intercalation electrodes with a sponge-like structure, as you see here shown schematically. Because we have to have the electron diffusion through the solid structure and the lithium-ion diffusion through the electrolyte-filled pore network. Additionally to the active material particles, we also have additives in the electrodes like binder, which provide the structural integrity and the substrate attachment. And we have conductive agents to provide or improve the electrical conductivity of the electrode. You see the structure of the electrodes is quite complex. And to produce such a lithium-ion battery, the process is also quite complex. Here I want to show you shortly a breakdown of the production process. And you see 18 different process steps, starting with the electrode production. Then we go into the cell assembly, and after that into cell formation. At last, we then do the module and system integration. And the question is, when we see this quite complex production process, how efficient do we have to be in each of those process steps to have an overall good efficiency in our process? Let me give you an example on that. Let's say we have an efficiency of 97% in each process step. So, for example, in the coating step, when we coat the slurry onto the current collector, only 3% of the slurry remain in the pot or get lost otherwise. And when we calculate this up for the 18 process steps, we get an overall process efficiency of only 57.8%. So more than 40% of all the materials and all the energy we put into the process are wasted. And that's a lot of waste, don't you think? So let's say we increase the efficiency of each process step to 99%. Then we get an overall efficiency of 83.4%. Much better, but not perfect. But the problem is, how do we reach those 99% efficiency in each process step? That's a very high efficiency. The best way to achieve high efficiencies in such process steps is to understand what is happening. What process parameters do influence my process and my properties of the product in the way I want them to. So we have to draw the process property relationship. But we have a problem because the direct connection between process and properties of our cells are very complex, and we basically have no essential understanding of them. But we can do a workaround. We can draw the connection between process parameters and the structure of intermediary products, like pore structure or mechanical structure of our electrodes, for example. And then we can draw the connection between the structure and the property. So we indirectly get our process structure property relationships. But you see, well, we have many process steps, and therefore we have many influencing parameters on the cell properties, like material parameters, voltage range, or additive content and type, and so on, which, for example, have an influence on the voltage curve of our cells, but also electrode production parameters, like the processing intensity, the material distribution, coating thickness, and so on. Or cell assembly parameters, electrode balancing, or which electrolyte and separator type we use. But this is not only a downside. As you see here in the Ragon diagram, we get a wide variety of performance parameters for our lithium-ion batteries. We have so many parameters, we can possibility between in the process and get largely different specific powers or specific energies out of our cells. So we can design our cell to the purpose we need. So much to the basic setup. Now I want to go deeper into the electrode production, and my colleague Ika Boiano will then later on go deeper into the cell assembly and cell formation. Okay, let's start with the first process, the dry pre-processing. The dry pre-processing mixes powder components before we do the wet mixing slurry production step. Important influences during this process step are stress intensity and number, the device type we use, and the geometry, as well as the components involved. As you see, for example, here in this diagram, when we increase the stress intensity, the possible particle size we can achieve gets smaller and smaller. And also for increasing dispersion time, we see the particle size also drops. The influence of the dry pre-processing on the properties of intermediary products, for example, the mixed powders or the slurry, are that the pre-processing allows for a very specific structuring of components. We can select the components we want for the dry pre-processing, and we can structure them in ways we cannot do in other processes. For example, intense pre-processing can lead to mechanofusion, as you see here in the SEM pictures. On the left side, we have a low intensity pre-mixing with large carbon black agglomerates between the active material particles. And on the right side, we have an intense pre-processing where we coated the carbon black onto the NMC active material particles, mechanofusion. But we have to be careful. Intense pre-processing can also lead to active material breakage. So the dry pre-processing can, on one side, simplify dispersion by doing particle structuring beforehand, but it can also create structures which are not possible during dispersion. There are a wide variety of possible devices and machines for the dry pre-processing. I just want to show you a selection here. For example, we can use a rotary drum mixer, which is a macroscopic mixture device which introduces almost no mechanical stress, but it improves the homogeneity at the beginning of the dispersion by doing the mixture of the dry components. Then we can use the Eirich mixer, which is a more intense mixing device and can disagglomerate, for example, carbon black particles, but also improves the homogeneity at the beginning of the dispersion. And at last, I want to show you the ring shear mixer. The ring shear mixer is a high intensity mixing device and can not only disagglomerate, but can also do the mentioned mechanofusion, but also potentially damage particles. Also, the ways to analyze or characterize our intermediary product, the dry particle mixture, are also multiple. So I just want to show you a selection here. For example, we can do particle size measurements, which give us information about particle structure and interaction, and also can show mechanofusion. So you see here in the diagram, this peak for the carbon black vanishes when we increase the rotor tip speed of the ring shear mixer. So we see there's no free carbon black anymore. Everything is coated. Or we can do TGA measurements, which give us also data or information about particle interaction by shifting the temperature of the mass loss to lower or higher values. We can do pugnometry measurements to get the density of our materials, or SEM images for qualitative impressions. And BET, which is also an interesting analysis method because it gives us information on particle structure and can show particle damage or delamination. As you see here, for high mixing intensity, we get a vastly higher BET surface, means some particles seem to be delaminated or damaged to create new surfaces. Okay, now we have done our dry pre-mixing. So now we are ready to do the wet processing, the slurry production. Important influences during this process step are mixing intensity and mixing time, again, order of component addition, device type and geometry, temperature, and the solid content. And all these process parameters mainly define three aspects: the component structure, the component interaction, and the component distribution. And these three aspects also have an influence on the formation of the conductive agent binder network, which is a very important structure in the electrode, simultaneously providing the mechanical strength and integrity and the conductivity of the electrode. And they have an influence on the viscoelastic behavior. And this viscoelastic behavior is quite an important property of our slurry because it defines, on the one side, the coating behavior during the coating step and the sedimentation stability. So the major influence during this process step on the properties of our electrodes is that the component structure and interaction is mainly defined in this step. Of course, the dry premixing has an influence on this, but this is the main step to define component structure and interaction. And as I said, the processability during coating is defined by the viscoelastic behavior. Again, there are multiple different devices to do the wet mixing. Just want to show you a selection here. So we can use a dissolver, for example, on a small to medium scale, is a batch production device and can handle low to medium viscosity. The energy input is on a low to medium level. The planetary mixer is a bit larger, on a medium to large scale, also batch production, can handle a bit higher viscosity slurries, and has a low to high energy input. And then we have the Eirich mixer again, which is not only a dry mixing device, but a combined mixing device. on a scale from small to large for batch production, can also handle low to high viscosities, and has a low to very high energy input. And at last, the one continuous slurry production device in this list, the extruder, which can handle medium to very high viscosities up to almost solid mixtures with very low solvent content, and can have a low to very high energy input. Analysis methods to characterize our slurry are, for example, the particle size measurement again, which can show us the progress of our dispersion process. For example, when you see here, the dispersion time increases, the particle size distribution changes. Or we do cryo-SEM measurements, so we cool down our electrodes very fast, for example, with liquid nitrogen, and then we freeze dry them and we get these pictures. So from these pictures, we then can draw information about the particle binder interaction. Or we do rheology analysis, which gives us detailed information on the component interaction. As I said, the viscoelastic behavior is a very important parameter. And for example, we can do shear rate or complex rheological measurements to give us information about the characteristics of our slurry. At last, I want to show you the solid content measurement, which is more of a quality and process control parameter. When we see that the solid content is not the value we want it to be anymore, something is off the rails and we have to check our process, because a change in the solid content also changes the viscoelastic behavior. So now we have finished our slurry, and the next step is to bring the slurry onto our current collector by coating. Important influences during the coating step are mainly the coating speed, the device type we use, and the interaction between the slurry and the substrate. And the main influences of the coating step on the electrode properties is that the coating is the most important step defining the area loading distribution of our electrode, and also the quality, because the quality of the coating device and the quality of the wetting of our slurry onto the current collector define the quality of our electrode later. So on the one side, we have to choose a substrate which is fitting for our slurry, and we have to see that mistakes we create during slurry production or coating, for example, if enclosed air by no sufficient degassing or large agglomerates or insufficient wetting, can lead to coating defects, which are exemplarily shown here, like free spaces or agglomerates. Devices used for coating are usually of two groups. On the one side, we have self-metered processes, and on the other side, pre-metered processes. During self-metered processes, the area loading and quality is mainly defined by the gap height between the coating knife and the substrate, the viscosity of the slurry, and the wetting behavior. These devices are usually easy to clean and handle and are quite flexible in using different slurries. So we can change from one slurry to another very fast without major problems. But the coating quality compared to pre-metered processes is lower. And it is an open system, so contamination is possible. Pre-metered processes, on the other hand, in this case, the area loading and quality is defined by the volume flow we apply from outside, the position of the slot die, so whether it is in 8 o'clock position or 12 o'clock position or something in between, then the viscosity of the slurry and the pressure loss in the slot die gap. These systems are closed, therefore contamination is not such a great problem. and they have a high longitudinal coating quality. If we want to achieve a high transversal coating quality as well, the slot die needs to be optimized for the slurry we use. So the slot die is not that flexible regarding different slurries, and it is much more complex compared to a self-metered process. This is why self-metered devices are usually used in research, where we want to coat different slurries on different substrates and want a fast change between them. And pre-metered devices are usually used in industrial processes where we have one slurry and produce kilometers of it. Analysis methods to characterize our wet film are, for example, gloss. Gloss is influenced by the component distribution and the coating surface, and a change in this gloss value can show us demixing or inhomogeneity. So it indicates mistakes in the electrode. Also, we can do automated defect detection, which is an inline quality control system and allows us also to automated wastage disposal or marking, but can also give us information on coating problems. For example, when we get the same defect over and over again. We can do inline NIR measurements to detect the wavelength characteristic in the IR spectrum. As you see here in the circled area, this is the peak for the water adsorption. And therefore, we basically get an inline residual moisture detection. Or we can do topology or coating thickness measurement, which gives us information about the coating homogeneity before we dry, so we get a very fast feedback on the quality of our area loading distribution. And so we can change process parameters if the quality is not right. Then we have Raman measurements, where we can detect different chemical bonds in molecules, which allows us for a component mapping in our wet film. After coating, we immediately dry the electrode to get the porous particle structure we saw at the beginning. And during this drying step, we have two major influencing parameters. First, the drag by the evaporating solvent, and second, the diffusion. The drag increases gradients because it drags lighter components like binder or conductive agents to the surface of the electrode, like you see here. The drag increases with higher temperature and airstream, so basically with more intense evaporation. On the other hand, the diffusion always decreases gradients. And so the diffusion also increases with higher temperature, but is comparatively slower than the drag. And this means that we get more intense gradients when we have more intense drying parameters, like you see here in the diagram on the right. When we increase the drying temperature and therefore increase the drying intensity, the adhesion, shown as the columns of the electrodes, decrease because we have less binder at the substrate for the adhesion and more of it at the surface. Methods to dry an electrode are basically of three types. First, we can use conductive drying. So we have a heated plate, lay the electrode on top and dry it. Or we do convective drying. Convective drying means we have hot air, like in an oven, and dry the electrode with that. Or we do radiation drying, where we have infrared radiation and with it heat the electrode and dry it. But on the horizon, there are also newly emerging drying technologies, which are currently in basic research, like laser drying or inductive drying. And each of these drying methods has their respective pros and cons. Conductive drying, for example, is quite simple, but not easy to scale and has no inherent vapor transport. Convective drying, on the other hand, is easy to scale up, has an easy inherent vapor transport, and allows for simultaneous double-sided coating, but it is quite energy efficient. So this is state of the art, but as you see, the energy efficiency is quite low. So many manufacturers of dryers for electrodes look at this radiation drying for the next step because it's also easy to scale up. It has no inherent vapor transport, but the energy efficiency is much higher and it is faster compared to convection drying. So there might be in the future a shift to radiation drying or a combination of both. Ways to analyze our dried or drying electrodes are, for example, area loading distribution measurements, which give us an idea of the homogeneity of the area loading distribution. This is important because the area loading distribution is quite important for the cell performance and especially for the balancing. Then we can track the temperature profile during drying. And as you see here in the diagram, we have the hot air temperature as dotted lines, and we have the electrode surface temperature shown as full lines. As you see at the beginning of the drying, the electrode surface temperature is much lower than the hot air temperature because of evaporative cooling. But then at some point during the drying process, the electrode surface temperature reaches the hot air temperature. And this means no significant evaporation is happening anymore. And so basically, this is the point where the electrode is more or less dry, not regarding residual moisture. We can also do pore size distribution measurements. Pore size distribution is a very important influence for the ionic conductivity of an electrode. And so this is a measurement which gives us the possibility to connect these process structure relations I spoke about earlier. We can also do some EDX measurements for information on the component structure or component distribution. We can do electric conductivity measurements because the electric conductivity of an electrode is also a very important parameter influencing the cell performance. And then we can do adhesion measurements because adhesion is relevant for the further processability of electrodes. After the drying, the next step is usually calendering. Why do we calender the electrodes? Well, basically, the electrodes after drying are functional electrodes, but usually we calender them for two reasons. First, being increasing homogeneity of the electrode, and second, being increasing the energy density, because during calendering, we compress the electrodes, decrease the pore volume, and therefore increase the mass per volume, and so increase energy density. During calendering, the most important influences are, on the one side, temperature. An increased temperature leads to a more elastic electrode behavior, and this means that we need less line load, less pressure to reach the same rate of compression for the electrodes. The other important parameter being, of course, the line load or the pressure. An increased compaction leads to a high energy density because we decrease pore volume, but very high line loads can also lead to particle breakage or even electrode damage. The main influence of the calendering step on the electrode properties being the change in electrode porosity. Well, when you look at this diagram, we see when we increase the compression of the electrode, the electric conductivity increases. This is because we increase particle-particle contacts. But at the same time, the ionic conductivity decreases because we decrease pore volume, which is very important for ionic diffusion through the electrolyte. And so we get an optimum behavior of our electrode performance. So we have to balance out the electric conductivity and the ionic conductivity to get a good electrode performance. But we also have to balance out this good performance against the energy density we reach. So that is always the question we have to ask ourselves. Machines to do the calendering are usually of two types. First being presses. In a press, we can do sheet compression. So this is more of a lab scale. We can do it hot or cold, and we have an aerial compression. So this process is pressure controlled. On the other side, we have calendars, which are continuous compression devices and therefore more on the industrial scale. Can also do hot and cold compression, but these processes are line compression processes. So it is quite difficult to calculate the pressure. So this is why the calendering process is usually line load or gap controlled. Analysis methods for the calendered electrodes are very similar to those of the dried electrodes, like adhesion measurements, which are relevant for the processability, but can also influence long-term cyclability, or electric conductivity measurements, where we see that calendering usually improves electrode conductivity. As you see here in the diagram, first the electrode resistance increases a bit because of particle rearrangement, but then we decrease the resistance of the electrodes by calendering it. We can also track line loads or the electrode thickness to get data on the plastic and elastic deformation behavior or deformability of electrodes. And we can again do SEM, EDX, or pore size measurements. Now the electrode band is finished, but one last step is missing, and that is cutting. So we have our electrode band, but to assemble cells, we have to cut the electrodes in the form we need it. So this can be done either by laser or by mechanical cutting. Laser cutting has less abrasion and contamination, has a longer lifespan, and is more flexible regarding electrode form. But the introduced heat by the laser can damage the coating if we are not careful, and this process is more complex. The mechanical cutting on the other side is cheaper to purchase, but can have metal abrasion and therefore metal contamination in the electrodes, and the mechanical cutting can lead to coating breakage at the edges. And now the electrodes are finished and ready for cell assembly. So thank you very much for your attention. That was quite a wild ride. I hope you could bear with me. If you have any questions, don't hesitate to ask.
Good afternoon to everyone. My name is Iker Boyano. I'm working in CIDETEC. I'm the team leader of the pilot plant, and I'm going to do the second part of this training that has started Robin. Brilliantly, Robin. I'm going to try to keep the level of the presentation, and at least I'm going to use the same format. That is a good point to start. The idea was at the beginning, Robin has explained us how is the electrode production with different processes of material preparation, coating, drying, or cutting. And now I'm going to speak about the cell assembly with the stacking, packaging, sealing, and with the forming of the cells and with the testing of these cells. The idea is at the beginning we have talked about how the electrodes are prepared, and now we are going to talk about how are the stacked. how is the packaging of these cells. Usually, the packaging is defined in 3 different formats. The first one is the soft packaging, in which they used a pouch or laminated cell, aluminum polymer laminated packaging. And this is used usually because this is easily adaptable to different dimensions of the cells and different capacities. You can change the number of electrodes, and the capacity of the cell can change. This is lightweight, and this is it has a good thermal behavior in large format. This is commonly used in research because you can adapt the cell for whatever you want. The other type of cell are the hard case, that is made of aluminum and stainless steel. It's about 1 millimeter or 2 millimeters thick. They have a defined structure, both prismatic and cylindrical. That is, from a point of view, or a numerical point of view, this is good because you have defined the stack of the module, because you have defined the structure. He has one of the pros is that the safety, because they have venting valve. If you have an event, is safer. But the cost and the weight is higher than in the soft packaging, and as we told you, is less adaptable to different formats. The difference between the prismatic and the cylindrical is the prismatic case has higher packaging density on pack. Okay, this is cylindrical, and when you have to pack it, you have less density. Well, nowadays there is a lot of information about this kind of cell production, of this packaging. I left you here some examples, okay, of, for example, large axial post cell that are made in Volkswagen, or the prismatic hard case that are with BMW. And this is very good to see. You can touch if they are in YouTube, then you can see them. And there are here some videos about the cylindrical packaging. There are some machinery that are sold, and you can see how these cells are produced. There is a lot of information in the net about this cell, or how the cells are prepared. I recommend one of these review of PEM made by Aachen University. I have taken some of the figures from that review to this presentation. I think it's very well done. And the thing is that this information is needed. That's the objective, for example, of the LiPLANET project. There are a lot of pilot plants in Europe, and we have information about what we are doing ourselves, but we need to know and compare with each other if the information, the thing how we did are okay or not. That's the objective of LiPLANET. That's why these training sessions are done, in order to share information. And for example, one of the tasks in this project was to create or to manufacture a similar cell in different pilot plants in Europe and compare them and see if they are comparable. The results were really good. The cells are really similar from each other, using the same chemistry and the same materials, and this was really good. But the best thing of that project, of the task, was that you are in contact with people that are working like you, and they have the same problems. Sometimes when you are doing something and you are facing new materials, new technologies, you are feeling sometimes like alone in the dark. And this information, if you share, the improvement in the cells and the technology is very high. Then that's why this training is made, and this information is shared. Okay. When you are going to start with a cell, or we are going to assemble a a cell, the first thing is the design of this cell. There is different tools to work with this design. For example, we can, one of the tools is the backpack software that is of Argonne National Laboratory, in which if you register, you can design your own cell, design the chemistry that we are going to use, saying the loading that you want, the formulation, and this software gives you the different values of the cell, and it is give you a very good information before you start. You will know what type of cell you are going to obtain, doing what one cell using one format or other. Another way to do that is, sorry, I'm going to take some water. Is you have your own simplified Excel file in which you put here all the information that you know about the weight of the ALF, the weight of the tabs, what are the specific capacity of the materials, and then you will have the final result of the energy density of the capacity of the cell. You can have two here, for example. You can see the distribution of the weight, and this is very useful when we are designing the cell. This is one problem. Here is one problem that always happens between the project manager and the one that is working the pilot plant, because they came to you, the project manager came to you and say, okay, we are going to do a very high loading material, and I need to minimize the weight of the current collector, and we are using a very thin current collector, but you are going to densify a lot the material, but I don't want any wrinkle in the current collector. Then working with the Excel is quite good, but sometimes you have problems that you face when you are working on the production of the cells. But these tools are useful to know how to start working with the cell. Another, I can say tool, but it's not a tool. Nowadays, it is very important, the digitalization of the cell, the modeling, that can help you a lot at the beginning to know how the cell works. It's true that you need a lot of information at the beginning about the materials, about the composition, the porosity, but after you have your ideal, you have modeled the cell, you can get a lot of information about what is the best option to get, what is the best loading to have one current or one discharge current, or for example, where you have to put the current collectors of the tabs, what is the best option to get the best cell. This is nowadays there are a lot of people working on that. I think in LiPLANET 2 weeks ago did another training on that, and there's a lot of people is working on that. That is very useful thing to design cells. Okay. The idea is when you are going to work with a cell, first of all you design it, and you have a standard your format. Okay, in our case, for example, this is one of our standard cell that is about 14 centimeter per 23 centimeter. And the idea is when you are going to do this cell, all the process that are doing to get this cell are focusing in this format. Then the coating is going to be the width that is needed for this format. The calendering is going to be the same, and the electrode cutting is just focusing in your format. The idea is to have the less scrap or less losing material when you are producing the cell. I'm going to start now with when Robin has left. Now he spoke us about the cutting of the electrodes. and I'm going to explain how we are working, what are the process that we are using to construct a cell. Okay, and I'm going to start from the cutting. We cut the electrode in a continuous automatic machinery, and they are losing about only 2% or 1% of the material, because this is designing for that. And the idea is we are cutting by one the electrode. Here is cut, and here we take a photo of it, and we have by smart vision, we have a tolerance of 100 microns, and the electrode is over this tolerance is throw up down, and if it's okay, we collect it here. The next step after the cutting is the cell assembly. Okay, the stacking of it. Then all the electrodes are taken, and we as a separator to stack the cell. Here, the first step is the position recognition. Always there is a pick and place in which they recognize the position of the electrode, and it put the electrode in the right place in order to get the stacks. Once you have the stack, you have the current collectors, and you have the final stack in order to do the welding of them. There are two different ways to do this stacking. Here in CIDETEC, for example, always we have worked with the stacking winding, that is with lamination. But nowadays we have a new machine that is in the dry room, that is the theta folding, and I'm going to try to explain you the pros and cons of each system. The stacking winding, it takes the individual electrode, and it laminates to the separator by hot pressing. It was about 110 grades centigrade, and it pressed about 75 kilograms. The stacking accuracy is very high, it's about 0.1 millimeter. And with lamination, you get a lower interface resistance. Okay, but the main drawback of this work is that you need a laminable separator. On the other hand, the theta folding is you place the electrode, but the stacking accuracy is a bit less, as 0.2 or 0.3 millimeters, and the interface resistance is higher than the stacking winding. But in that case, it's not necessarily a non-laminable separator. That's why it can be used. Sometimes there are separators that are not laminable. Then it's another way to work with. In both cases, it happens that you need a continuous separator. You need a roll of separator. To work with these systems, automatic systems, is not possible to work with separator sheets. That sometimes happens that someone wants to work with a separator sheet, then it's not possible to do it automatically. Okay. When you have the cell pouch, the stacking, then you are doing the packaging. For doing that, the first step is the tab welding. You can do it using ultrasound or laser welding. We are using ultrasound, and you, depending on the number of tabs, depending on the material that you are using in the current collector, you have different welding protocol. And just at the same time, you are doing the deep drawing of the aluminum foil. As I told you, I'm going to explain you how we work with the aluminum foil with the pouch format. Okay, you do the deep drawing depending on the number of cells or depending on the thickness of the stack. The deep drawing is thicker, and the limit usually is about 6 millimeters of the deep drawing. Nowadays, there are materials that get higher than this drawing is about 10, 12, but the usual limit for this material is 6 millimeters. You do the insertion of this material, of this stack in the pouch foil, and you do the partial sealing of the pouch using the thermal sealing. Okay, you left one of the one side, you left the open. Well, we left it open just to dry, to put the electrolyte inside. Okay. The next step is the electrolyte filling, in which you took the cell. Here the cells have to be dry. We used to dry the electrodes before and after. We dry the cell and the stack and the before the electrolyte filling. We do the electrolyte filling, okay, in a special machine in which you do it. This electrolyte filling, you do it in vacuum. Okay. The idea is you put the electrolyte there and you go to different levels of vacuum in order to do an active wetting of the porous material of the electrodes of the cell. Then, when you have the protocol that you do for your cell, you take out the cell and you get this cell with here for the forming protocol for the casing, and this is sealed. All the cell, you have all the electrolyte inside, and the cell is sealed. Once you have this cell, you have to take care. The previous step was all the steps are important, but from the electrolyte filling, you have activated cell. Then you have to take care and take care of the cell and of the safety, for safety reason, because then the cell can have problems if you don't use it properly. Then you are going, when you have the cell, you go to the formation step, and this formation is a first charge that you do a charge a very low C rate. Okay, in that point, it happens. The C formation, and in which there are some gas can appear with this C formation. Depending on the chemistry that you use, this forming process will be different, and if this process can be affected by the temperature or by the pressure. The thing is that on client, on industrial partner has his own protocol. You can change the pressure, you can change the temperature, you can change the procedure to change the change, or you can change the additive that you put in the electrolyte just to do this forming and this forming process. Once you have finished this forming process, you do the gassing. Okay, you take the cell and in this part you put vacuum again, and you are doing that. All the gas is going out of the cell. You seal it again, and you cut this part, and then you have the final cell. I have another video of this process that show how does it done. I think that video is ours, and you will see how we do the degassing process. After the degassing, it's important to have an aging process of about more than 24 hours and check if there is a change in the resistance or change in the capacity of the voltage of the cell, just to check if everything is correct and there are not any reaction there in the cell. After that, you do the grading of the cell, you charge and discharge again, and if you have to ship it again, you have to ship to a client or to someone. Usually, you charge to 10–30%, and you send it to your client. But on the other hand, if you are not going to send it, but you have to test it at home, we can say, you can test it, but you have to take into account different things, because, okay, you can produce a lot of cells, but you have to take care of if your, for example, if you want to check the cyclability of this cell, you have to choose what are the proper C rate that you are using. If you are using C/10, you have to notice that it will need 1 month to do 30 cycles, and if it's going for, you can say, for 1,000 cycles, you need a lot of time and for this channel. Another thing that you have to take into account is, for example, depending in the cell that you are constructing, if your cell is about 30 ampere-hour cell and you are going to do a 2C test, you need a 60 ampere-hours channel. Then you have to take into account these all things when you are going to test the cells. Okay. It's not easy, but you have to take care of it. And it happens to us, okay, we are in a research center and produce a lot of cells, but from different chemistries, okay? And you have to take care of the safety of the cell. The people that is in charge of the electric lab always is, we can say, afraid of what chemistry or what kind of cells we are giving to them, because they are new cells and they are going to test, but we have to take into account that these cells have a lot of energy inside, and in case of event, we can have problems in the lab or with people. Then we have to take care and take into account this sort of thing. And the last slide is going to talk about that. Okay, now we in this training we show that how we start from materials and how we finish with the final cell and how we test it. But there are a lot of things, a lot of protocols, a lot of process that is not only how the cells are done. It has to be with the how you do the things. For example, things that are not very important, like how you handle the cell or how you transport it in your own place, are important. You have to define it. You have to do the protocols just to be sure that everything is safe. You have to take care of the number of channels that you have to do this kind of testing, or how much test you can do. You have to take care of what you are doing with your final cells. It happens to you finish with the cell, you have your testing, and after that, what happened with these cells? Some of them, they are in the 80% of the capacity. They have some degradation. Then you have to store it in a safe place, taking care of it, and you have to develop a protocol on what you are going to do with that. And another thing that is very, very important when you produce of cell is the traceability of the all electrode, the material that you receive, what are the electrodes that you have done with it, where you have stored this electrode, how long that you have stored, when you have do the cell, in what conditions, and what is the final result of the cell. And you have to test in this cell if everything is okay. Then it's not only do the cell, is how you do this cell. Okay. And this is sometimes takes more time than the production of the own cell. Finally, and as a conclusion, it says there are a lot of processes. Robin has shown one part of the process that you need to produce a cell. I will try to show you the other part of the process that you are needed for produce a cell. There are a lot of protocols that are needed to do there, but there is one part that is the machinery that is needed. Sometimes it's have a lot of cost. You need a big investment to do that. If you are working in a research center or in research, this machinery have to evolve with the technology that nowadays every year we have new chemistries, new format, new loadings that we are getting. Then this machinery have to evolve too, and we have to take care of the safety, and we have to share the knowledge. There is a lot of knowledge here in LiPLANET. There's the people that is involved. There are more lines that are working in this project, but this is one of them. And this is a lot of knowledge to share without, but this is a lot of knowledge that is needed in your own place, because as people here, for example, it's people that is from chemistry, it comes from chemistry, they're engineers, as people that knows about rheology, people that are characterization, people that now is mathematics or comes from physics, or all this knowledge is needed to develop new cells.